If we strip away all of the advanced features of modern ECUs, really the two key elements the ECU is in charge of are supplying the fuel and ignition to the engine. These are the two aspects that we as tuners need to control to be able to make the engine produce good power reliably. We're now going to look at tuning each of these elements separately, starting with the ignition. When we're adjusting the ignition table, we're setting the point in the engine cycle where the spark event occurs. This is known as ignition timing or ignition advance and refers to the number of degrees of crankshaft rotation relative to TDC on the compression stroke that the spark event will occur. In most instances, the ignition event will occur before the piston reaches top dead center on the compression stroke, and hence the numbers in an ignition table are normally positive values. A negative value would suggest that the ignition event has occurred after the piston has gone past top dead center and is moving back down the bore on the power stroke. The ignition angle is critical to getting the most power and torque out of the engine, and with the aid of a dyno, it's quite simple to set it correctly, as we'll see shortly. In order to understand what we're doing by tuning the ignition timing, we need to understand what's going on inside the combustion chamber during the combustion event. Most people assume that when the spark event occurs, an explosion takes place inside the combustion chamber. This actually isn't the case, and under normal combustion, we get a relatively slow combustion process taking place. What happens is that the spark ignites the air and fuel closest to the spark plug. From here, a flame front travels out through the combustion chamber, igniting the unburned fuel and air ahead of it. The result is a smooth and gradual rise in cylinder pressure as the combustion process takes place. What we're trying to do is time the spark event so that the combustion pressure peaks at just the right point in the engine cycle to provide maximum torque to the crankshaft. The point where we want to reach peak cylinder pressure is approximately 16 to 18 degrees after TDC as the piston begins moving back down the bore. It's at this point that we can achieve maximum mechanical leverage from this pressure acting on the top of the piston and being transferred down to the crankshaft. And in turn, if we reach peak cylinder pressure at this point, we'll see maximum torque and power from the engine. If we start the combustion event too soon, the expanding gases will actually be counterproductive. They'll be pushing on the top of the piston while it's still trying to come up towards top dead center. On the other hand, if we start the combustion event too late, the piston will already be moving back down the bore as the gases expand, and very little force will be transferred to the piston. To demonstrate this, let's look at a graph of the pressure in the cylinder during a combustion event. Let's start by seeing what happens to the pressure in the cylinder if we have the ignition set correctly. In this instance, the correct ignition timing happens to be 30 degrees before top dead center. You can see that the pressure rises smoothly as the piston comes up past TDC before peaking at approximately 16 to 18 degrees after TDC. The pressure then smoothly decreases as the piston moves back down the bore and the volume in the cylinder continues to increase. Now let's look at what happens when the ignition event happens too late. We refer to this as retarded timing. In this case, the ignition event has happened at 16 degrees before top dead center, and we can see that the combustion really hasn't had much time to get going before the piston has moved past top dead center and started moving back down the bore. Now the expanding combustion gases are effectively chasing the piston back down the bore, and because the cylinder volume is constantly expanding as the piston moves back down, we don't see the same sort of cylinder pressure as we did in our last example. Remember, it's this cylinder pressure that acts on the top of the piston and is transferred into the conrod and then finally the crankshaft, generating torque. So if the pressure in the cylinder is lower, we won't see as much torque from the engine. Lastly, let's look at what happens if we start the spark event too early, which is known as advancing the timing. In this case, the spark event occurs 35 degrees before top dead center. Now we see the cylinder pressure begins rising while the piston is still moving up the bore. This becomes counterproductive since the pressure is now fighting against the piston, making it harder for the piston to make its way up to TDC. The net result is that if our ignition timing is too far advanced, we'll see the torque output actually drop as the cylinder pressure fights against the piston on the compression stroke. So the key to tuning the ignition timing is to choose the correct ignition advance so that we reach peak cylinder pressure at the optimal point in the engine cycle. Unless we're working for a well-funded race team though, we're unlikely to have the benefit of in-cylinder pressure transducers so that we can see what the cylinder pressure is doing. Remember though, that the cylinder pressure affects engine torque, and if we have the engine on a dyno, then we can measure this torque. What we want to do is begin with very conservative or retarded ignition timing, and then adjust the ignition timing until the engine torque is maximised. This point is known as MBT, which stands for maximum brake torque timing, or minimum timing for best torque. Let's stop for now and have a look at this concept being put to the test with a dyno demonstration.
To help illustrate the technique of tuning the ignition timing in the ECU, as well as the effect the ignition timing has on engine torque, we're going to perform a demonstration now using the torque optimization feature on our mainline chassis dyno. For this demonstration we're using a Toyota 86 fitted with a Motec M150 ECU, but as usual the concepts are applicable to any engine and any ECU platform. We'll start with a quick tour of the relevant features of the Motec ECU software, and here we have our ignition timing table. And this is a numeric table of our ignition numbers, our ignition advance angle. On the x-axis here we have our engine RPM, and on the vertical axis we have manifold pressure. To the right of the numeric table we have a graphical representation of the ignition table, so we can see the general shape of the table. Now for this particular test I'm going to remove the graphical elements, so we're just looking at the numbers. What we're going to do is concentrate for this test at running the engine in this particular cell here, which is 2,500 RPM and 60 kPa, and we're going to do that in 4th gear on our dyno, so I'll just get the engine running now. Now before I start this test, we're going to retard the timing so that we know that we're well below MBT timing when we start this test. So what I'm going to do is I'm going to highlight the cell that we're interested in as well as all of the surrounding cells, and I'm going to set them all to 10 degrees of ignition advance. The reason I'm choosing all of the cells around as well is because this makes sure that we're not going to be interpolating from the surrounding cells. It makes our test more accurate. Now we've got our engine running, let's have a look at our mainline torque optimization test software. So here we've got a test that's going to graph torque versus ignition angle, and on the bottom axis here, our x-axis, we have our ignition timing value. Now this is just being transferred through from the ECU. On the vertical axis here we have the torque being measured by the dyno, and then we have some live values being displayed here in the top right corner. So this includes our ignition timing, our current torque, our engine RPM and our throttle position. So what I'm going to do is I'll make sure we're central in that 60 kPa zone now, and I'm going to click begin, and then I'm going to simply advance the timing at about 1 degree a second. And what we're going to see while I'm doing that is that the dyno will plot the torque relative to the ignition timing. And what we're expecting to see here is as I move the ignition timing, I advance the timing, I increase the timing. We've got that ignition event happening earlier, and our peak cylinder pressure is occurring closer to that correct optimal point in the engine cycle. We're going to see our engine torque increase, it's going to peak, it's going to then plateau, and then it will finally fall away as I continue to advance the ignition timing beyond MBT. So we're up to 30 degrees now, and you can see that the torque increase has actually stopped, and we're pretty well plateaued now. We haven't really seen much of a change between about 30 and about 35 degrees there. And we'll continue though all the way through to 50 degrees, so we're coming up now towards 40 degrees. And you can see that the torque is actually falling away now. As I advance the timing further, we can see that the torque is dropping off, and this is simply because now the peak cylinder pressure is occurring too early in the combustion process, too early in the engine cycle, and it's becoming counterproductive. It's working against the piston while the piston is still trying to come up the bore. So we're getting all the way up now to 49 and finally 50 degrees. Okay, we'll shut the engine down now so we can see the result of that test. And you can see that displayed on the dyno now. We have our little crosshairs which show us the point at that particular zone in the ECU's operation, 60 kPa and 2,500 RPM. At that particular site in the ignition table, we achieve MBT timing at 33 degrees. So 33 degrees of ignition advance, 33 degrees before top dead center, and we saw at that point 103 Newton meters of torque. Now, the important thing to note here as well is that the actual torque tends to plateau. So we see early on in the test when we're a long way away from MBT, so particularly between 10 and 20 degrees of ignition advance, we see a very sharp increase in torque per degree of ignition timing. Now that's an indication that we were starting a long way away from MBT, so anytime we see a very large increase in torque for 1 or 2 degrees of ignition timing, that's a hint that we're a long way away from MBT. You can see though, as we get closer to MBT timing, the increase in torque as we add timing becomes less, and we get to this point where between around about 25, 28 degrees and about 35, 36 degrees, we're really not seeing much, if any, in the way of torque change across that point. So what we're doing when we're tuning the ignition timing is we're choosing the ignition angle when we first see that torque value peak. That's the MBT point, which stands for minimum timing for best torque, or also known as maximum brake torque timing. Now, of course, for the purposes of this test, our engine is not knock limited at this particular operating point. So I'm free to advance the timing all the way to 50 degrees and the engine is not suffering from knock or detonation at this particular operating point. Of course, if the engine was knock prone, then we may not be able to reach that MBT timing point, which is why it's important to monitor knock or detonation while we're tuning the ignition table.
There are many factors that determine the amount of time between when the spark occurs and when peak cylinder pressure is reached, and we'll discuss these now. First up, we have the diameter of the cylinder. It takes a certain amount of time for the flame front to travel across the cylinder, so the larger the cylinder diameter, the more ignition advance we'll need. Smaller cylinders, on the other hand, require less ignition advance. Next, we have the compression ratio of the engine. As the compression ratio increases, the air and fuel molecules are squeezed tighter together. This lets the flame front travel through the air-fuel mixture faster than if the compression ratio was lower. This means that the actual combustion happens faster, and hence the cylinder pressure increases quicker. For this reason, as the compression ratio increases, we'll need less ignition advance. The design of the cylinder head and combustion chamber will also affect the ignition requirements of the engine. Take an engine with a centrally located spark plug, for example. This lets the flame front propagate evenly in all directions, so combustion happens relatively quickly. On the other hand, if the spark plug is offset to one side of the combustion chamber, it takes longer for the flame front to reach all of the air-fuel mixture, and the engine will need more ignition advance. Lastly, forced induction has a similar effect to increasing the compression ratio. There are simply more air and fuel molecules in the cylinder, and they're packed together more tightly. This means that combustion happens faster, so we need less ignition advance. The more we increase the boost pressure, the less ignition advance we need. Let's have a quick summary of things so far. We're trying to find the amount of ignition timing we need to get cylinder pressure to peak at around 16 to 18 degrees after TDC. We've learned that combustion does take some time, and the speed of combustion will depend on a number of aspects, including cylinder diameter, compression ratio, the design of the cylinder head, and whether the engine is using forced induction. This information helps us understand why different engine designs need different ignition timing. We also need to be aware that the correct ignition timing is a constantly moving target, as it will depend on the engine RPM and the amount of load or airflow through the engine. There isn't a single fixed value that we can apply for ignition timing and expect optimal performance from the engine. This is why we have a three-dimensional table for ignition timing, so that we can adjust it to accurately suit the operating conditions of the engine. Let's consider what happens as we increase engine RPM. We already know that the combustion event takes a finite amount of time, and we're trying to time the spark events so that we achieve peak cylinder pressure at about 16 to 18 degrees after TDC. As engine RPM increases, this means that we need to advance the ignition timing because there's less time available for the pressure to reach its peak. Here is a graph that shows the general trend that we get. As the engine RPM increases, we see a trend where the ignition timing advances. The other trend we see with ignition timing is that it will vary with the amount of load the engine is under, or to put it another way, the amount of air and fuel being combusted. At idle or cruise, for example, there isn't a lot of load on the engine. This means we have a limited amount of air and fuel being combusted in the cylinders, and in this situation the combustion event will take longer. For this reason, at light load or low throttle openings, we need to begin the ignition event earlier in order to reach peak cylinder pressure at the right point in the engine cycle. At wide open throttle, however, we have a large number of fuel and air molecules tightly packed together in the combustion chamber, and hence the combustion event happens much faster. In this situation, we don't need to begin the ignition event as early in order to reach peak cylinder pressure at the right point in the engine cycle. If we consider a full power run through the rev range of an engine, even under wide open throttle conditions, the amount of air entering the engine is constantly changing, which affects the ideal ignition timing too. The engine's volumetric efficiency will typically be lower at low RPM, rise and peak as the RPM climbs, and then drop off again at high RPM. The volumetric efficiency describes the amount of air entering the engine, and the shape of the VE curve under wide open throttle will look similar to the engine's torque curve. As the VE or airflow increases, we need less ignition advance because the combustion happens faster. Likewise, at low and high RPM, where the VE and hence airflow are lower, we tend to need more ignition advance. If we plot this trend, forgetting for a moment that we're also changing the ignition advance in relation to RPM, we get a trend that looks a bit like this. You can see that we have more ignition advance at low and high RPM, but less around the area where the engine makes peak torque, because this is where the engine is combusting the most fuel and air. So these are the two trends that we have affecting the ignition timing as we move through the rev range, and if we combine them, we get an ignition curve that looks something like this. We can see that the ignition advance increases as RPM increases, but we can also see that there's a reduction in ignition advance around peak VE or peak torque. At this point, hopefully you'll be able to understand why the correct ignition timing is never a single fixed number, but rather a constantly moving value that depends on the engine speed and load. This is why it's essential to have a 3D ignition table in the ECU to properly set the correct ignition advance. When tuning the ignition table, we use the technique I demonstrated on the dyno to tune each cell in the 3D ignition table. If we do this throughout the engine's operating envelope, we can be assured that regardless of what RPM or throttle opening we use on the road or the track, the ignition timing will be correct, and hence the engine will be producing maximum power and maximum torque. Here's an actual ignition table we might expect to see in an ECU. It's represented as a 3D graph, which makes it very easy to see how the table changes to account for both RPM and engine load. This is the sort of ignition timing I'd expect to see from an engine that has had the ignition timing tuned correctly. There's been a lot of information to take in this module, so let's have a quick recap. To summarise, we want to start the combustion event so that we reach maximum cylinder pressure around 16 to 18 degrees after TDC, as this will give us the most amount of torque from the engine. The amount of ignition advance we need to achieve this will depend on the engine RPM and load, as well as various engine design parameters such as the cylinder diameter, compression ratio, and spark plug location. We find the correct ignition advance by using a dyno and advancing the ignition timing until the torque reaches its maximum. This point is called MBT, which stands for minimum timing for best torque.